Hello again, guys. There was an issue with the computer in my previous video. I was talking about standing waves in pipes closed on one end and open on both ends. If they are closed at one end, remember you have a quarter of a wavelength here. You will have a quarter plus half a wavelength. That will give you 3/4. Here you will have 3/4 plus two, yeah, basically 2/4 or 5/4. So 1, 3, 5, 7, etc., etc. For the open on both ends, you have first, second, third. So the length here, right? For this one, your lambda is equal to 12 because the length is half a wavelength, if you think about it here. Here you have a full wavelength. So the length is equal to lambda. So the fundamental frequency is n over 12 times v. All right? In the third harmonic is 12 divided by 3, if you think about it. Right? So you have here a wavelength plus another half. Plus, how will you guys see this? I mean, you can just substitute here, you get 12 over 3, but peak to peak. Mm, 2 over 3 equals to lambda. Oh, yeah, so lambda is so 3/2 of L equals to 3 lambda halves. Yeah. Okay, so we have that. Yeah. Lambda plus half a lambda here. Yeah, that will give you 3/2 lambda. Sorry, sometimes you know have to be careful how you see this. It doesn't matter because you're gonna use this equation at the end of the day for the open. It's the same as the standing wave. And that's basically the idea behind standing waves for open pipes or closed pipes. Let's do a problem so you guys can see how this is done. Now I had to restart my computer because for some reason it froze. I don't know it had to do with the mouse not working, but it happens. Um, so we're in sound. And this is the last topic before we go into light, which I think is an easier topic. The problems are a bit more interesting as well. Okay. A pipe open at both ends has a fundamental frequency of 260. What's the length of the pipe? So fundamental frequency is at n equals to 1. So 260 equals to n over 12. Um, Times v. So at 0 degrees, you want to know the speed of sound. So we go back to the slides. It's about 330. So 331. So 260 is 1 over 12 times 331. So 12 is 331 over 260. So we use the calculator to find that. .64 meters. That was it. What's the fundamental frequency at 30 hertz? That will be 343. So you want to find F when V is 343 and you already have the length of the pipe from Pare. That's just that. This one is Doppler effect. Again, think about it, right? You have an airplane traveling at half the speed of sound. So half of 343, that's the speed of the source. And is emitting a sound at this frequency. You have the stationary listener. So in here, let's actually do this one. The new frequency will be 1 over you can use the same, right? V plus or minus U observer, V minus plus U source multiplied by the 4.22. That's the frequency, the theoretical frequency. V will be the speed of sound. Plus or minus is the you observe, but the observer is stationary, so this is 0. V is the speed of sound. Which one do you use, minus or plus? Since the airplane in part A is coming towards the listener, V minus U of the source is half the speed of sound. So this will be 343 over 343 minus half of 343. 171.5. Well, I mean, obviously what we're gonna get here, right? All of this is gonna give you 2. 2 times this. So 8.44. 8.44 kilohertz. All right. For part B, the airplane is now away. It's moving away from the listener. So instead of using minus, use plus. It's the same idea, but it will be lower than 4.22. So that's what I'm gonna do in this video, and with the previous video. You have 2 good videos of sound, standing waves, some examples of Doppler effect. I will do another video to finish with this, and then there are already videos about refraction, reflection of light, lenses, mirrors. Take a look at those video lectures, and then I will upload more videos with more examples as we go throughout the weeks. So have a nice rest of your day, guys, and I will see you guys on the next one. Bye-bye.